heard from Mark, we will have more people here, which is good news. Maybe plus 4 to 8 people, something like this. They allow more people in. Well, we'll start the lecture with a quiz, and we typically will start the 2-hour-long lecture with a quiz. The quizzes are going to be on the material of the previous lecture, so today's quiz is on the material of the previous lecture. So here is the question. A small reminder about usage of clicker. You should register to frequency AB, which is done as follows. Long press on off button, then A, then B. So please do it right now before you start collecting the answers. It should flash a green light or something like this. Okay, now we are ready to collect the answers. So when you are ready, click on one of the answers. The question is which one of the following is an equation of a plane that passes through point 1, 1, 0 and is orthogonal, which means perpendicular to this plane. X plus y plus z is equal to 5. And let's say we will stop at 4 minutes. So 4 seconds. Maybe let me guide you a little bit. You do want to eliminate kind of really impossible answers. And there are two conditions which should be satisfied by the correct answer. First condition, the point 1, 1, 0 should lie on the plane. Second condition, the plane should be orthogonal, which means perpendicular to that plane. So this, about each one of the options, you might want to check two things. Is the point on the plane? Is the plane orthogonal to the other plane? And you can change the answers just the last 3 counts. So we'll stop the system in a couple of seconds. So if you haven't yet, please press anything, because well, we do take points for participation as well. Okay, so I'm stopping the system right now. The correct answer was the most popular, well, but not convincingly the most popular. So, I'll show you the statistics. Here are the statistics. Let me explain the logical equation and how it works. For each one of the planes, we should check two conditions. One is the point on the plane, second is it orthogonal to the other plane. Let's eliminate some answer. A. Well, is the point on the plane? I should plug in x equal to 1, y equal to 1, z equal to 0 and check whether this equation is satisfied. Well, it isn't. 1 minus 2 times 1 is not 4. So it's not A. B. 1 plus 1 plus 0 is equal to 2, so, well, maybe for now. Point is there. Let's check the other ones. C. Well, z is equal to 0. Yes, the point is there. So right, maybe for now. D. Y minus z. So 1 minus 0 is equal to 1. Once again, maybe. And E. 1 minus 1 minus 0 is not equal to 2. So no. So just the point eliminates two options. We are left with three options. Well, how do we eliminate between those? We should check whether the given planes are orthogonal to whether these planes are orthogonal to this one. Well, how do we check that? We want to check the normal vectors. Are the normal vectors orthogonal to each other? What are the normal vectors? Here, the normal vector is 1, 1, 1. Here, the normal vector is 0, 0, 1. Here the normal vector is 0, 1, minus 1. So these are the normal vectors to the three planes B, C, and D. I want to check whether they are orthogonal to the normal vector of that plane. 2, 1, 1. Well, are they? Well, no. Not for B, not for C, yes for D. So 1 minus 1 is equal to 0. So the correct answer is D. Okay. Hold on. While I'm still here with my computer, let me show you. Something cool. So I tried to draw the saddle surface that we talked about yesterday, and I want to show you the traces. So if you recall yesterday's lecture, this surface had parabolas, inverted parabolas is one kind of traces, other kind of parabolas, upward parabolas is other kind of traces, and hyperbolas as the height traces, xy traces. So here we see I'm not sure which one is it x, z, or y, z, but one of the vertical traces, inverted parabolas, as you see. So you see, as you move the plane, the section changes. It's an inverted parabola, it becomes lower and lower, up to here, and then goes higher. In other direction, we should see, well, this kind of parabolas. So you see, as you move this plane, farther and farther from us, we see the parabola getting higher, then getting lower once again. It disappears over there. And finally, XY traces we cut by horizontal planes, and that's maybe the most kind of funny shapes. You see these hyperbolas, and you see this funny phenomenon. You cut by a plane which gets higher and higher, and the section becomes, well, first it is such kind of hyperbola, then becomes, well, you see the two branches almost merge, then they do merge, and then they separate in different directions. And you see this hyperbolas. So just wanted to show this animation. And yes, and please look at the saddle. It looks like this. We'll see it once again today. So this has some kind of such picture of a saddle in mind. Last time we started talking about functions of two variables. So, variables. We started talking about graphs of functions of two variables. So if you recall, a function of two variables takes in two numbers, x and y, and outputs a third number, usually referred to as f of xy. We've seen some examples. Well, first of all, we agree that in order to visualize how this function behaves, it is sometimes useful to imagine that it is kind of height function. So if you imagine your xy plane being the floor, with each point on the floor having its own x and y coordinate, the value of the function will measure the height above the floor of a point on this graph. So if my function at this point, I don't know what the x and y coordinates are, maybe x is equal to 1 and y equal to 5. If f of 1, 5 is 2, then the point on the graph will be right here. Then I change my y, my value of the function maybe becomes lower, so here's a new point. Then it becomes even lower, so here's a new point. I step here, maybe it becomes higher, so I get a point. And together all these points will they form some kind of surface. This surface is called the graphable function. And we've seen an examples of graphs functions. So here's my function x squared plus y squared. What is the graph? Well, it's a surface where for each point xy, the z coordinate is equal to x squared plus y squared. And we've seen last time that the shape of the graph is a paraboloid like this. So for instance, you see, well, some features like where is the smallest value of my function? Where is my function the smallest? For what value of x and y is my function the smallest possible? Well, you look at this paraboloid, you just want to find the lowest point on this paraboloid. You call that my function value is just the height of the point on the graph. So you look at this paraboloid, the lowest point is right here at the origin. And of course it is confirmed by the algebra. What is the smallest possible value of x squared plus y squared? Well, this number is always positive, and it is exactly 0 at the origin. When x is equal to 0, y is equal to 0, and hence x squared plus y squared is also 0. Other examples. F of x comma y is x squared minus y squared. Once again, it is a function which we already have seen the graph of. So the graph, if the surface z equals x squared minus y squared, and we've seen this surface a couple of minutes ago. In fact, the way to reduce the surface on the computer is I asked the computer to plot the graph of the function. So, x, y, z. So, which way the cell goes, and if I fix an x, it's inverted up. Okay, so it looks something like this. So a saddle like this. And now notice, well, now we do have points both above the floor, above the xy plane, and below xy plane, which is reasonable. Look at this function. If x is larger than y, the function is positive. If x is smaller than y, the function is negative. So we should expect points at a positive height, so somewhere here, and at negative height. If you move along the y-axis, well, the function becomes more and more negative. We also see that this function doesn't really have a minimum, or doesn't really have a maximum. We can imagine that it goes as high as we wish and as low as we wish. If we continue going in this direction, the function becomes more and more negative. In that direction, it's more and more positive. Yeah.
Does it switch into an upside down parabola towards the end? Because it's... How does it move?
All these sections are upside down. All these sections are facing up.
Okay.
So it's kind of facing up like this, and then facing down like this. So it's such kind of shape.
Okay.
I wish I had a saddle, but I don't. Okay, so we've seen such a graph. There is another graph which we also have seen. It's a graph of the following function. F of xy is square root of 1 minus x squared minus y squared. Well, this function looks more complicated. What is the graph? In the surface where z is equal to square root of 1 minus x squared minus y squared, what is this function? What is this surface? Well, as it's written right here, we haven't seen such a surface, but we can do a simple algebraic manipulation. Write it as z squared is equal to 1 minus x squared minus y squared, or x squared plus y squared plus z squared is equal to 1. Now it becomes a familiar surface. What is it? Sphere. The sphere, in fact, of radius 1. So let's try to sketch the graph. Well, all I have to do is just sketch the sphere. Okay, so if you imagine that this is a sphere. Well, it's kind of graph of this function. In fact, not quite. Why not? Look, a graph of a function is something that shows above each point x, y what is the height, and this height measures, well, what is the value of the function. What can we see about the value of f of xy on this picture? So fix some point x, y. So in this plane xy, fix some point. Something in this plane. So this point is not on the sphere, it's in the plane xy. Its height is equal to 0. Now, the value of the function at this point is the height of the graph above this point. So, what is it? I can go up until I hit the sphere, or I can go down until I hit the sphere the second time. So right here, if I measure the height, well, it might be something like, well, in the picture it looks like 0.6, something like this, or minus 0.6. Which one is it? A function is something that takes in two numbers and outputs just one number, not a couple. It cannot tell you the function cannot tell you my value at the point, well, 0.3, 0.7 is either plus 0.6 or minus. No, it should decide. The function assigns one value. So such a surface cannot be a graph of a function. We made some mistake. Where was the mistake? Let me give you a one-dimensional analog. If I want, so analog graph of x, which is equal to the square root of 1 minus x squared. What is the graph? It's y equal to square root of 1 minus x squared, or in other words, y squared is equal to 1 minus x squared, or x squared plus y squared equal to 1. Well, it's a circle. But once again, the same problem. A circle is not a graph of a function. Graph of a function should assign to one value of x just one value of y, not two different values of y. So what is the problem in both of these?
There are two answers for the square root.
Yes, exactly. So I can go from this line to that line, but I cannot go backwards. If I know that z is the square root of something, yes, I do know that z squared is the square of this, but I can't go backwards. When I take a square root, I should choose either positive or negative square root. So here I should remember that this equation holds, and also that I'm choosing the positive square root. And then my graph becomes an actual graph. So I should not see anything with z which is negative. So this is the wrong answer. The correct answer is a hemisphere. So it's the upper hemisphere, kind of kept like this. Now it does look like a graph of a function. For each point x, y, I can see what is the height above this point. Similarly here, this is the wrong graph. I should have only taken the upper half circle. Maybe any questions about these graphs? Like what they mean, why they look the way they do. Okay, so let me talk about domain of the function. You see, these two functions are quite different from that function in the following sense. You can take any two numbers x and y and plug into these two functions. They will produce you some number. You can't really do this with that function. You can only plug in numbers x and y which produce a positive answer under the square root. If you get something negative, then you'll try to extract the square root from something negative. Well, you get something which is not a real number. So let's talk about the domain of a function. It's the set of values, the set of points x, y, can be at which the function can be evaluated. So, like for a function of one variable, say if you want to talk about square root of x, you should remember that you should not take x to be negative. So there is a domain to this function, positive reals. Here the domain is, well, not as simple. It's the set of points where the function can be evaluated. And these points are points in the plane. So let's have some examples. Domain of this function is the set of points x, y. So let me just try this equation. All points x, y, where this thing is positive. If this thing is negative, I cannot evaluate my function. I want always to take square root of something positive. In other words, x squared plus y squared is smaller or equal than 1. Well, what is this thing? You can sketch it. X squared plus y squared equal to 1 is the circle, union circle. If I want x squared plus y squared to be at most 1, I should look at the inside of this circle. So that's the domain of my function. Of course, the function can be more complicated than that. Let's say something like this. Another example. F of xy is logarithm of xy. What can I say about the domain of this function? Greater or equal than 1? So it can't evaluate logarithm of say 1/2. So you say that I cannot evaluate logarithm of something which is more than 1, like 1/2, 1/2. Greater than 0, yes. So if I want to evaluate logarithm, I want to make sure that the argument of this logarithm is positive, strictly positive in this case. So domain, I want to make sure that xy is positive. Well, still a complicated condition. I can't really imagine how it looks like, but I'm almost there. Xy, well, the product of two numbers is positive. in two cases. Either both of them are positive or both of them are negative. So this is equivalent to saying that x is positive and y is positive, or x is negative and y is negative. Now I can try to imagine how this region looks like. So it's a union of two subregions. This region, where both coordinates are positive, that's called the first quadrant. And the region where both coordinates are negative, that's called the third quadrant. And also, I don't want to include the boundary. I don't want to include points where x is equal to 0 or y is equal to 0. So in the picture, I'll draw something like this, a dashed line. So now the domain of this function is this region, a union of two little quadrants. Well, we can imagine that questions? You can imagine the domain of a function can be a little arbitrarily complicated region in the plane. But basically the procedure is just look at what can prevent you from evaluating the function. You want to evaluate logarithm, we'll make sure that the argument is positive. You want to evaluate square root, make sure that its argument is positive or 0. You want to divide by something, make sure it's not 0. And so on and so on. Okay. Now let's talk about slightly different way to visualize functions. So we've seen this way of drawing the graph of a function. There is a problem with it. It's quite complicated. I mean, even the simplest functions, those functions, it wasn't the easiest task to draw the graph. It's more complicated, it's even more complicated. So we'll borrow an idea from kind of cartography. Suppose you have some region with different heights, like a region with several mountains, several maybe valleys. You want to draw a map of this region and you want to tell people, well, how high will they have to climb from this point to that point. What you do is draw some kind of what's called topographic map. It looks somewhat like this. So here's the topographic map of a mountain, and it goes something like this. You start at sea level, height is equal to 0, then you go to 500 meters, then you go to 1,000 meters, then you go to 1,500 meters. So here's an example of a mountain drawn. On a map. You look at this map and you can tell what it means. You see a mountain, somewhere here is the top of the mountain, and you see, well, what are the curves where the elevation of the mountain is 0, then 500 meters, then 1,000 meters, then 1,500 meters. So maybe let's also draw some kind of lake here. will be z equal to minus, well, I chose a step of 500, which is not reasonable for lake. Well, let's pretend it's a really steep lake. So here's a lake. On this map, here's the line on which the elevation is minus 500 meters. So it's some kind of such a surface. So you see how to go, well, as you go on this region, you see how high you will be at each point. If you want to climb the mountain on a steep hill, well, probably you'll choose this hill. In a short amount of kind of distance, in a short distance, you climb lots of elevation. If you want less steep hill, maybe you'll climb this way. So you cover the same elevation but over much longer distance. So you see, well, some features of the terrain, some features of this region. That's exactly what we want to understand about the function. How fast is it growing? How fast, well, where is it the highest? Where it is the lowest? So we'll produce a kind of topographic map of this function. This trick is called drawing the level curves. So we'll talk now about level curves of a function. So what happens is, given a function, I want to understand on what points in the plane the value of my function is, say, 0. On what points the value is equal to 1. On what points the value is 2. And then I'll plot all these different curves where my function is equal to 0, where it's 1, where it's 2, and so on. And then I'll try to see whether I get the picture of how my function actually behaves. So let's do some example. Here's a function f of xy is 1 over x squared plus y squared. Let's try to see what the level curves are. First of all, I want to think about some level. Level is kind of the height. I want to choose the value of my function to be some number z0. What is the curve on which the value of my function is equal to this z0? Well, I want the value of my function to be exactly z0. Let me manipulate this equation a little bit. X squared plus y squared is 1 over z0. And now I see it is a circle of radius 1 over square root of z0. So let's see what the level curves are. I'll produce a sketch. It will be a two-dimensional sketch. I'll only plot x and y coordinates, and the value of my function will be, well, indicated on this graph. So let's look at the level curve at height 1. When z0 is equal to 1, it's a unit circle. So that's the level curve z equal to 1. Then we continue making the same step in the height and plot the level curves. So let's choose the step to be equal to 1. Let's plot the level curve when z equal to 2, then z equal to 3, z equal to 4, and so on. Z equal to 2. We should draw a circle of radius 1 over square root of 2, something like 0.7. So on this circle, the value of my function is 2. Let's continue. Level curve z equal to 3, 1 over square root of 3, well, something like 0.6. So here I have z equal to 3. Z equal to 4, well, circle of radius 1/2. Then I'll have circle of radius 1 over square root of 5, square root of 6, square root of 7, 8, 9, and so on. So the circles will become denser and denser. I mean, if I want the circle, if I want, say, a circle of radius 1 over 4, it's level curve number 16, where z is equal to 16. So there should be 16 circles that between this circle and the circle of radius 1/4. So now we just have 1, 2, 3, 4, 5, 6, 7. So it should fit into 9. So you see the circles become denser and denser. What? Yes, and we can try to go backwards, like lower the elevation. But now we have a problem. When the node is equal to 0, what can you say about this level curve? Nothing. There is no level curve. My function is never 0. I cannot divide by 0. What happens when the node is -1? Once again, nothing happens. There is no level curve at height -1. I cannot take square root of -1. So my function is in fact always positive. So now we can try to imagine this function. What is the behavior? Well, in this region, it should be smaller than 1, but still positive. So it is kind of some number between 1 and 0. Well, some numbers. As you come closer and closer to the origin, as you climb this mountain, well, you get higher and higher. Right here you are at height 1, height 2, height 3, height 4, 5, 6, and so on. So if you imagine kind of what kind of mountain has produced this map, you'll be forced to think about some mountain like this. So here it is almost on the board, on top of the board. As you come closer and closer to the origin, the height above the board is larger and larger. So you should imagine some mountain peak like this. So the corresponding graph might look somewhat like this. So you'll have a peak, a very high peak near z equal to 0, and you'll have level curves which are circles like this, which will become lower and lower, but never will become negative. So the height is never negative. And you do see that this thing kind of explodes. At x equal to 0, y equal to 0, it goes all the way to infinity. It becomes larger and larger. Well, to be honest, even producing such pictures can be quite hard. I mean, it at least involves drawing lots of curves. And drawing curves is something complicated. Remember in 104, you probably spent quite a bit of time in drawing implicit equations. So given an equation, try to find out something about the shape. So that's exactly the task that we have to do, but quite a lot of times. We should produce lots of level pairs. Sometimes they are familiar, like circles. Sometimes they are not as familiar. What is good about such a picture? Well, once you have this picture, it's quite easy to imagine how the function looks like, how it behaves. Imagine seeing a picture like this. This is almost the kind of picture that I want. It is a set of level pairs of some function. What can we say about this function? Well, unfortunately, with no extra labeling, we can say only a little bit. You can see that it could be a map of a mountain like this, another mountain like this, and maybe it goes down in these directions. Well, maybe. Why do I say maybe? Because just as well, it could be a map of a valley, like this, maybe a lake, and another lake right here, and then two mountains going up right here. Both kinds of terrains will produce the same kind of maps. So without the extra labeling, well, you see that there is something happening. So you see that this is either a mountain or a lake, and this is either a mountain or a lake. And here we have the functions either increasing or decreasing. So it's changing, you don't really know in what direction. If you have also the labels, something like z equal to 1, so let's say 5, 0, 1, 0. Well, now the picture is much more clear. Now my function, well, first of all, you can read off the value of your function if you want x equal to 4. This value and y equal to that value. The value of your function is the height at this point. What is it? Well, somewhere between 4 and 3. Somewhere between this level curve and that level curve. So the value of the function at this point is probably something like 3.5. Another thing, if you want to go from this point in the direction where the function increases, well, you should go in this direction, towards the mountain top. Here you have another mountain top. Here you have some kind of valley. Here you have some kind of point where in this direction the function increases, in that direction the function decreases. And they are kind of familiar with such kind of points. It's a saddle point. Point where in one direction the function increases, in another direction it decreases. So such pictures can be very useful for analyzing how a function behaves, understanding how it looks like. Okay, so yeah.
What function do those level curves represent?
So I did not tell you what the function is.
Okay.
So the function, I didn't write down the function. I can give you an example of a function which produces a similar picture, maybe. But it doesn't matter. My point was, even without the actual formula, you can understand how this function looks like, how it behaves. I mean, I can try to produce a formula which will correspond to such a picture. Maybe I won't try to do it on the spot, but I mean, you can imagine that there is some function which produces such a picture. It's like with graphs of function environment, one variable. You can draw different kinds of curves. Well, they correspond to some functions. Not always they correspond to some function which has simple formula. but nevertheless they can be used. Okay, so let's take a break.